I was told to give a presentation on the life cycle of stars. This isn't going to be a normal presentation. This is going to be a 5-minute lecture. So if anyone has any question, please wait. There's going to be a frequently asked questions section at the end of the presentation. Just a quick 2 minutes for anyone that has anything or any problem that they found with the presentation that I'm going to give. This is the life cycle of stars. I've asked many people in my life, where do they think the stars come from? After all, the nearest star to Earth, the sun, is responsible for pretty much all the life here on Earth. Without it, there wouldn't be life on Earth. Sadly, they couldn't answer where it came from. So hopefully by the end of this presentation, you'll be able to find out. Stars, all stars are made of gas, primarily hydrogen gas. The reason why it's made of hydrogen gas is because it's a very intricate, chemically, hydrogen gas. As stars are made of gas, it has huge quantities. Hydrogen gas is the most abundant gas in the universe. All stars exist within dark and cold clouds that expand rapidly, being added onto by dying stars, having hydrogen gas within them. Dust and hydrogen gas exist in huge quantities in the universe. The cloud wants to dissipate, just like any smoke here on Earth. But the gravity always wins. This is a rule of thumb in the world of astrophysics, that gravity always wins in conflict. Gravity always wins. The matter crunches inside of that cloud, crunches down into its basic form. It tries to form a circle. Anything above the diameter of 134 kilometers wants to form a circle, and this is what happens to take place. More and more gas gets pulled into as it becomes a more and more spherical shape. More and more mass exists within one spot. It begins to have a gravitational field. It begins to pull the rest of the cloud in with it. It begins to heat up. It begins to get denser. And at 18 million degrees Celsius, the transformation takes place. The hydrogen atoms in the star's core begin to bind together, which is something that's called nuclear fusion. This is something that we're trying to mimic here on Earth at the moment. And with a burst of nuclear energy, the star begins to shine. It blows away the gas. This is a star in formation in the middle here. It blows away the excess gas and dust away from it, leaving the star itself the shine of the newborn star. Now here's something that we need to wrap our heads around. The relationship between the gravity of the star itself and the amount of radiation that it needs to give out in order to counter the power of gravity. This is gravity versus radiation. It's very simple. A new star, and for a good few billion years, can reach hydrostatic equilibrium. Not every star can reach it, but we'll talk about that in a bit. If you take a look at the following picture, you'll be able to understand it better. The star itself wants to condense deeper and smaller into a smaller space. This is how gravity works. But at the same time, as we talked earlier, hydrogen atoms within the core of the star itself wants to push out. It binds together, releasing energy, pushing away the surface of the star. Now this happens, and this continues for billions of years. The sun has been in hydrostatic equilibrium for billions of years, and it will continue for billions more. A vast majority of the hydrogen gas reserve gets eaten away through the time. Now this is a problem, because the more it eats away, and by the way, the sun kind of consumes trillions of kilograms of hydrogen gas every minute. You can kind of imagine how that works. And until it reaches a critical point, the point at which the radiation pressure from the nuclear fusion in the middle of the star can't really keep up with the force of gravity, as it's very constant. At the point, as we talked earlier, the rule of thumb, gravity wins again. The star starts to fail to dish out enough radiation to counter the tremendous force of gravity. And before you notice it, the star begins to collapse. Now here's the problem. It explodes in a supernova. A supernova is the most powerful explosion in the universe, possible even in the universe. These are the only explosions that we've encountered so far. But if we look at it mathematically, there should be a higher tier of them a hypernova, but we still haven't counted them yet, so we won't even talk about them. This is the universe in a picture. Quite basically, this is where our sun is. We'll begin it right here, since this is what we're familiar with. This is where our sun is. Now, if we take a look, this is hydrostatic equilibrium. It is very stable, it is very nice and warm, basically, and it can have a star system around it. It can have a few planets revolving around it in something that's called a Goldilocks zone. This is where Earth is. The Goldilocks zone is the area, the diameter of the orbit around the star that a planet can exist in. It can have warm enough temperature for the water to exist and not evaporate, but it won't be cold enough that it would melt, that it would freeze. A few billion years from now, approximately 3 to 4 billion years from now, our sun will transmit from a main sequence star into a red giant. Now this is a scary phase, because at the red giant phase, the sun will begin to expand. The problem is, it's not going to expand a few kilometers on each side. It's going to expand enough that it will actually be inside of the orbit of the Earth itself. Mercury and Venus and Earth itself will be scorched by the heat of the red giant now. Now here's the fun thing. This is the star shedding its excess mass. It failed to continue to dish out enough radiation pressure to counter the force of gravity. It has excess mass that it can't keep. So it pushes it all away and leaves behind a white dwarf. This is where our sun is heading. It's a very small star, really, really smaller than the parent star. It's a lot more dense. It has somewhat of the same mass. Well, not somewhat of the same mass, but it's kind of close to it. And over the years, it can't dish out enough radiation pressure to keep hot. So it changes color to white. And over a few hundred millions to a billion years, it will turn into a black dwarf. It's just useless. You can live on a black dwarf, which was previously a star. But here's the fun thing. A red giant can also, if it has enough mass, it can explode in supernova. We just talked about this. It's a very bright and interesting explosion. The reason why it's interesting is because every single element on a periodic table that we have known can be made from a supernova. Think about that. After a supernova, it begins to be quite annoying to do the math, as we're dealing with really big numbers, 10 to the power of 13, and things of that sort. It can have one of two outcomes. It can either be a neutron star. The star itself collapsed under its own weight, but it could at least keep itself together. The few atoms that remained kind of got squished together, broke free, and only the neutrons within the nucleus of the atom remained. Everything else just flew away. Now this is posing a problem to physicists because we don't know what the core is. We don't know what's in the middle of it. We know that the stars have gas in it, hydrogen, helium, iron, silicon, any of that. But the neutron star, no one has any idea what's in it. We believe it's some neutron degenerate matter, but we have never experienced it, and we have no idea to tell. The other possible outcome is a black hole. During this year, or during last year, we attempted to take a picture of the black hole. In the upcoming year, 2018, we'll be able to see our first picture of a black hole. The reason why it's called a black hole is because it has a gravitational field so strong. All of that mass collapsed into a single point. The density became infinite. Gravity became infinite. It's called a black hole because it's the only object in the universe that light cannot escape. If light passes near it, it will be pulled in towards it, and it cannot escape it. There is this hypothetical limit outside of the event horizon, which is the point at which light can exist. Basically, not get sucked in, but it cannot leave. Because at the event horizon of a black hole, the escape velocity, which is the speed you need to achieve in order to leave that mass, the massive object, is at the speed of light. Light can't exceed the speed of light. Nothing can exceed the speed of light. So if you go near a black hole, there's no way of coming back. Another possible outcome of a supernova is the planetary nebula. Now these are the beautiful pictures that we see online. These are pictures of a very colorful and pretty gas clouds. It's made of hydrogen gas, helium gas, and a bunch dust. The problem is with the nebula is that, well, not the problem, this is the fun thing about the nebula, is that after the supernova, this is what makes this cycle continue. This is the excess gas from which it all began. This is the starting point. It turns into a dust cloud. And then it takes the rest of the cycle from a protostar to a main sequence star. Now this is the fun thing, the brown dwarf. The brown dwarf, as we talked earlier, a star needs to achieve hydrostatic equilibrium in order to maintain its own weight, in order to not fall. But what if it doesn't maintain hydrostatic equilibrium? What if it doesn't achieve it at all? This is what happens. It just fails to dish out enough radiation. The mass just condenses into one spot, and it just remains a brown dwarf. This is the twin of this, the black dwarf. This is the universe. Now here, let me leave you with one ending point. This is going to be the end of it. One ending point. We talked earlier about the supernova, and we said that every single element in the supernova from the periodic table is named. Let's take a look at the elements that made us, that made life. Hydrogen comes from a supernova. Carbon comes from a supernova. Oxygen comes from a supernova. We feel special because we look at the supernova and see it's special. It's different from us. We feel belonging to it, and we think it's special because we're different from it. But let me leave you with this. We are made from this. Maybe we're not special because we're different from it. Maybe we're special because we're the same. Thank you for listening.